Well, Joseph Kursky here, and myself, along with my colleague Kansarina Kurnia, welcome you to another edition of our Higher Education Chats. Kansarina and I have been looking forward to this for quite a few months now, because we've got two of our wonderfully expert, but also wonderful teaching colleagues here. We've got Ankita Bakshi and Jie Liu from our spatial statistics team, but they do so much more. Some of you probably have seen them both on various Esri plenary videos in the past. They are wonderful, and we're very happy to have them to talk about spatial statistics, why to teach with these tools, how to teach with these tools. So I'm going to turn it over to my colleagues now. Again, folks, thanks for teaching this chat with us, and thank you all for joining.
Thank you, Dr. Kursky. Hello, everyone. I am Ankita Bakshi, and as Dr. Kursky mentioned, I am a product engineer on the spatial statistics team at Esri, and I'm joined by my colleague, Jie.
Yeah. Hi, everyone. Yeah, my name is Jie. I'm Ankita's colleague, and I'm very happy to have our first work day of 2020 with you guys. 2022.
2022. Wow, this is the first time I'm actually speaking it out loud, so that's interesting. But yeah, thank you everyone for joining us today. So today we are going to talk about what's new with spatial statistics tool in Arcgis Pro. And to get us started, just want to quickly talk about what are spatial statistics. I'm pretty sure many of you are working with spatial statistics tools, or might have used statistics, or are teaching statistics, or GIS in general. But to kind of give a sense what are spatial statistics and what domain we are kind of working on. Basically, what we are trying to do is turn data into information using statistics. So let's say I give you this spreadsheet. Is it data or is it information? I mean, a raw data or a raw spreadsheet might not help us make any decisions. They will not help us make any policies, any decisions, because it's just a lot of data. And with the recent advancements in storage and the way that we are collecting data, that data is just growing exponentially over the years. So how to turn this data into information is where the expertise of spatial statistics come into play. If this spreadsheet is just given to someone like this is definitely data, because you cannot really tell anything about it unless you do something with it. And the first thing, if we just think about it, if we just put these points or this data on a map, we start visualizing this data. Even though we start visualizing this data, our brain has to do a lot of information. We have to figure out what that information is. Our brain is doing a lot of interpretation. Are these areas of high densities, low densities? Our brain is doing a lot of that that chunking of that information. So here's where spatial statistics can help you. It can help you take that data and it can help you make that decision. So in that spreadsheet that I showed you earlier, the easiest thing to kind of start understanding the data, the information from that data would be to do a min, max, standard deviation, mean, average, these things, so that you can start getting that information. And spatial statistics is very much analogous to that, where you kind of start quantifying the things that you are seeing on the map. So you see these patterns, but are these patterns really the patterns that you can make decisions based off of? There is more to that than just what the eyes are seeing. It's quantifying those relationships that you're visually seeing on a map, or sometimes you're not even seeing those relationships visually, because there's some hidden information that we can extract from that data, and that's when spatial statistics can help us get that information. And spatial statistics doesn't exist in vacuum, but it does it follows a workflow. That workflow really starts with kind of getting that data, understanding that data, cleaning it up, which kind of we refer to as data engineering, kind of engineering your data to make it better for your analysis, because your analysis is as good as the data that you provide. So kind of taking that data, visualizing it, exploring it, then doing some spatial analysis, and then as a part of spatial analysis, you can do machine learning. You can use some algorithms to kind of extract that information from the data that you have. Then you can model, script, and share and collaborate, because sharing is such an important piece of like decision making, because if you've got the information, if you know what patterns you're seeing, but to kind of help make that decision, to kind of help spread the awareness, you need to have that sharing and collaboration piece. So basically, spatial statistics is kind of like a part of that bigger process where we start understanding sharing and making decision part. So there are a lot of new things in spatial statistics. So we're like 2 releases. This is just like 2 releases stuff that I've put it on a slide. And there's a lot of, like, we have data engineering, spatial association, spatial outlier detection, time series smoothing, presence only prediction. There are a ton of things that new tools and technology that has been added to Arcgis Pro from a spatial statistics standpoint. But for today's presentation, we're just going to focus on these 4 tools, because in the interest of time, we can only pick a few. And change point detection was something that was requested from one of you, so we added that here. Data engineering is very special to us. Like, this is completely new technology and some interesting things about density-based clustering with time and presence only prediction. But if you're interested in any of the other things that are mentioned here, at the end of the presentation, we'll share some blog posts with everyone. So if you're interested in looking at other things, you can look at those blog posts. But to start off, we have data engineering. It's kind of counterintuitive that I'm talking about data engineering in a spatial statistics workshop or a spatial statistics chat. But if you think about it, like, we are the biggest consumer, and we have to, like, if you're doing analysis, you have to make sure that the data is correct, that you have the right data to do the analysis that you're interested in. So, like, a lot of our colleagues, including myself, we put in the work to make this data engineering process a little less painful, because it's like, mostly when you're doing analysis, this is the part of the analysis that takes like 80% of your time just to get the right data, just to clean it up and understand that data set. So what we are going to do in data engineering is getting our data ready for analysis. And some of the questions that we can ask ourselves, like, what does my data look like? Kind of start exploring that data. What's missing? Is it anything wrong with my data set? Can I add more information? Like, can I enrich it? Can I add more demographic information to help me do analysis later? Or should you transform that data as like a normal distribution? Is it good enough for the analysis that has this like underlying assumption that the data has to be in this format? So the best way I can like talk about data engineering is through a demo, like a quick demo, to kind of help us understand what things this data engineering can help us achieve in Arcgis Pro, and with a few examples. But once we are done with this data engineering thing, like, then we kind of get into the fun stuff, because like, for me, the fun stuff is like the analysis part, it kind of understanding the data, crunching those numbers. So yeah, so to get us started with what data engineering is, I'm going to show a quick demo in Arcgis Pro. So here, to kind of understand the example, what I have here is, this is a map of San Francisco, the city of San Francisco, and there are some points on the map, and each point on the map represents an affordable housing project. So there are some these projects in the city where like each project has several housing units, and each project has some housing units that are affordable, some housing units that are at market values, to kind of understanding what that data set is. If someone gives me this data set, I don't know much about it, and how I can start exploring this data set and cleaning it up for my analysis. So to open data engineering, there's a dedicated view in Arcgis Pro where we have combined different things that exist already in Arcgis Pro, added a few new things to help streamline this data preparation tasks. So to open that view, what we can do is right-click on this layer, and then we can go to data engineering. So once we click on this option in the right-click menu of your layer, you kind of see this new view that pops up in your in your project. So once you open it, first of all, you'll see this list of all the fields that this data set contains. So here I have 72 fields or attributes that each of these points on my map contains. So information like project ID, status, street name, what is the dates of the insurance, the issuance of notice period. So like I said dates. The reason I said it because like these icons really help me understand the type of that field. So if I didn't have that information, I would not know like the issuance of building permit. Is it like a text field that has the permit, or is it the date when the permit was issued? So these like these icons really help me start understanding like my data and what type of fields I have. So here, another thing that I absolutely love about it is I can quickly explore my data set using these like hover buttons. So let's say I can update the symbology of my map based on this field project type. So if I click on it, I can start seeing that some of these are rehabilitation, some of these are new construction areas. So kind of start exploring like what this project type mean in this data set, or affordable units. Let's say like how many, these are the places that have the highest affordable units in my data set. So if I zoom out a little bit, we'll start seeing and understanding like what each of the field has and what does it represent and how it's spatially distributed. So I really love the fact that you can just start exploring your data quickly. I mean, definitely it's not a replacement to like the great maps and symbology that people use to create beautiful maps, but really helps you start understanding your data a little better. So once you've kind of understood what the fields are, you can dive it deeper into these fields. So what you need to do is select the fields that you're interested in. So right now I just selected all my fields, dragged and dropped them to the right, and then I click calculate. So once you calculate for each field, the data engineering view gives you the quick statistics, like what are the minimum, maximum values, standard deviation, mean, all the way up to some sophisticated statistics like skewness of the field and kurtosis of the field. So basically, when I get the data set, I really like to look at the null values, like are there any null values in my data set? So if there are any null values, then I can right click and either like select them, visualize them on the map, or fill them using fill missing value tool. So it really helps you assess the data quality. So if there are too many null values, there's something wrong with the data that you have. So you should not just like use it in your analysis without understanding why those null values exist. So one of my favorites are these chart previews. Like that really just helps me visualize each field easily, like without having to create charts, like 72 charts for each field, but really helps me kind of look at what the distribution is. So here I have, let's say this field, like planning case numbers. So it kind of helps me understand what the values in this field have, like kind of glimpse or like a summary of what the values in the field look like. So it's really interesting because you can start seeing these patterns. And then if you're interested in looking at this chart and kind of interacting with it, all you need to do is like right click and open that chart, and then that chart opens and then you can interact with it. It's like a regular Arcgis Pro chart, so it gets added under the layer. So it's very easy, so you don't have to create charts for each of the field, but you can create charts for the fields that you're interested in. Here, I think one of the interesting things is that I can, like using the filters, I can only look at my date fields. So here, what I'm looking at is my date field. So here I get the information of minimum, maximum values, like when was my notice period issued for different projects that I have. So just kind of starting understanding the pattern, and you can see the minimum and the maximum date values of each of the fields. So it's very, very interesting to look at those results. I can also look at some numeric values. So let's say I'm looking at this affordability field. I don't really understand what this field says, so I can open a histogram to see what this affordability index is. So here I see like this is kind of a bimodal distribution, which really means that some of the projects that I have in here Some of them have less than 50% as affordable units, and some of them are like over 95% affordable. So basically, some of the units are just for affordability and some of the units are at market rate. So if I had to kind of use that information in my analysis, like because it's bimodal, I can reclassify it. And using the Reclassify field tool, what I can easily do is, I quickly did it, so I'm just going to talk about it a little bit. Like when you right click on any of the fields, you get a subset of tools to do specific things for data engineering. You can clean, you can construct new fields, you can integrate some other fields, or you can format your field. So here, what I really want to do is I want to reclassify and this chart, like I need to reclassify this field. So what I do is I reclassify it, and once I open it from the right-click menu, like things like input table, the field, everything gets populated by the tool. So all I need to do is I have to tell that I have to manually reclassify my fields. And then if I say if it's 50, then it's mostly affordable. So the projects that have, it's like mostly market rate. So if a project has less than 50% of my houses that are affordable, so that project is at mostly market rate. So if it's 100 upper bound, so if it's between 50 and 100, that is mostly affordable. And then all I need to do is just like run this tool. And once I run this tool, new values or new fields will get added in my data set that I can quickly use in my analysis. So I'm just showing like bits and pieces of things that you can do. But if you have a workflow that really helps you clean it up, prepare your data, and use it for analysis.
Ankita, Joseph here, just while that's crunching away, what does the clean function do?
Oh, at the top of your screen, like you also see a ribbon with a subset of tools. So they're just like tools that are available in Arcgis Pro to help you like delete a field that you think it's not of the relevance, or you can alter the field. You can project like your
okay, so clean is like the all-encompassing sort of bin into which these go. Got it.
Absolutely.
Thanks.
Like these are like clean, construct, integrate, and format. These are like bins that we have created to bring some of the tools that are there in Arcgis Pro, but then these tools are just, you need to know them to find them. Instead, like we have kind of put them together to help you streamline the process, and you don't have to like search for these tools because these are very inherent to the data engineering process. And yeah, once the tool, the Reclassify tool, was executed, we have these two new fields. So if I just add them in my statistics, and I scroll all the way to the down to see where these fields are, now I see that here I can open this bar chart to kind of understand that now I have reclassified those like histograms that you were seeing into this text field to kind of, now you can use it in your analysis. So yeah, these are some of the examples that you can use data engineering for, to kind of clean up, understand, fix some values in your data set. So yeah, that was a quick demo about data engineering. And we have a blog post that has this example with more information and more things that you can do. And we'll share that at the end of the presentation. Like you can go through that blog post and go through the workflow if you're interested. But kind of switching gears from data engineering to more spatial statistics tools. So here, like in the beginning, I kind of talked about that we were going to talk about data engineering and then some of the new tools in spatial statistics. So here I have density-based clustering as a tool that I want to talk about, but this tool has been in the software for years, and it's like one of the most heavily used tool because people use it all the time to find spatial clusters. What we have done recently is kind of added time in the analysis. So density-based clustering, now you can find clusters in your data set, not just based on where they are located, but also when that event happened. So now that tool has been enhanced, like the two methods that the tool has, dbScan and optics. These are the two methods that you can use to kind of cluster or find clusters in your data set. But now you can incorporate time in the analysis. To kind of just get started about time, we kind of have to talk about the time when we didn't have temporal analysis in it, like what used to happen and how the clusters were created in space. So in density-based clustering, you can create clusters or regions or groups of your features that are in high density regions, and then mark the points or the things that have happened but are in low density regions as noise. So basically what you have, like, let's say you have events, you have crime events happening in a city. So you can find the clusters where like the most crime incidents have happened and where they are clustered. Similarly, like if you have taxi pickup locations, you can find where are the clusters where people are taking taxis every day, where are those like spatial clusters, but also you can incorporate time, like at what time of the day those clusters are located. Is it at the beginning of the day, at the end of the day, in the middle of the day? So kind of incorporating space and time really helps you refine your analysis. So to find the clusters in dbScan, what it does, it finds the locations or the incident points that are in high density region, and it marks it as a cluster. And the points that are in low density regions, and it will be marked as noise. So how do you define a high and low density region? That's all the analysis that you are working on. Like you need to define what you consider to be a high density region. So you can tweak it, you can tweak it using these two parameters in the tool. So the first one is the search distance, and the second one is the minimum features per cluster. So in the tool, you can use these two parameters to define your area of high or low density region. So let's look at a quick example here. I have these two different regions. Let's say I define a search distance of 10 meters, and then minimum number of features per cluster is 10. So in the example on my left, I have a point of interest, and I looked at the search distance, like a 10-meter radius of that point, and I did analysis, like, do I have at least 10 points in that search distance? Because I've defined the 10 meters and 10 as my number of points that I need to be in a cluster. So since both of the conditions are met, this area will be defined as a high density region. Similarly, for this example on my right, within the search distance, I do not have 10 features. So this will be classified as a low density region, and hence this will be marked as a noise. But I said earlier that you could tweak what a high density and a low density region is using these two parameters. So let's say in this example, I said that I need at least 5 features to be considered as a cluster. In that case, the second example would be a high density region, because it is based on the parameters that I gave to the tool, this is a high density region. So you can tweak and find clusters what you consider as a high and a low density region. So once you've identified the region, like this is a high density or low density region, how does a cluster grow? It's very easy. I'm just going to quickly go through a couple animations here where I have this point of interest and my search distance is 5 meters and the minimum number of features I need is 5. So here, this point of interest, using these two parameters that I have, it says that yes, it has 5 features within 5 meters. So this will be marked as a core point. So the way the algorithm progresses is for each core point, it will add that core point and the points around it in a cluster. So these points are now a cluster. To grow the cluster, the algorithm, what would it do? It will take a neighbor in the core point and it'll do the same analysis. So this point, look at the search distance. Are the 5 features met? Yes, then it is also a core point. So it kind of keeps on growing the cluster, because like this is the area where like all these points are densely populated, or these are clusters that are just together. So it's a high density region, and all these points make up that high density region. And at the end, like if you have a point in your cluster that is not a core point because it doesn't have the 5 features within its neighborhood, then that would be considered as a boundary point, and you wouldn't grow clusters beyond your boundary point. So here, all these points are core points. So all these points are clustered together, but the points that are outside that high density region are marked as noise. And the algorithm just like does it for all the features in your data set. So here we have your clusters, and the noise points are also marked. But when time is added, there's a little addition to when the time is added. Here you have a point, and then that point also has a temporal neighborhood. So earlier we only said 5 meters, but here we also have a temporal neighborhood of 4 days. So the points that are before or after the 4 days of that point of interest are your neighbors. So all the points that are not in that time zone of 8 days, 4 before and 4 after, are dropped from the analysis of that point, and then the algorithm just keeps on working the way it used to work in space. So here, again, you just keep on increasing and creating clusters. So the difference now we see is that these clusters are more refined. So when you also add temporal neighborhood, these clusters are refined. They're just not in space, but also the spatial and temporal clusters. And there's another option to use optics in the tool. So optics is different from dbScan in the sense that dbScan really helps you find clusters of same densities. So cluster 1 and cluster 2 will have similar densities. If cluster 2 has is less dense, it will not be marked as a cluster. But with optics, what you can do is you can find within your study area places that are of high and low densities, and also find clusters with different varying densities. So the concept is very much similar. You find the search distance, and you find the minimum number of features in your search distance. So here I found that 5 features within a smaller core distance. But in this other example, I found 5 features in a bigger radius. So you can see like both of them have 5 features, but on the left, the core, the location or the distance at which I found 5 features was, let's say, 2. And in the right example, the location or the points at which I found minimum 5 features, the distance was 7. So now the densities have varied. Like this, both of them are clusters, but then the one on the left is more dense, the one on the right is sparse. So even if these two are clustered, you can find clusters with varying densities. So all we need to do is, for each point, we find the core distance, like the distance that it took to find those minimum number of features. And once we plot those distances on a reachability plot, you can say when those clusters are found. So when you plot these distances on a reachability plot, the points that have a smaller core distance are clustered together, and the peaks here, the peaks are the distinctions between the clusters. So these clusters, these points that have small distances will be clustered together. The points that have a jump is a different cluster. But with optics, we can tweak the clusters. So to tweak the clusters, what we can do is we can increase the sensitivity of the cluster. So here I see that there is a potential to break these clusters into 2. So in the tool, I can increase the sensitivity, and I can say that split this cluster into 2, because there is, based on the reachability plot, and seeing there could be 2 clusters. So that was a lot of information, but I think that can just like help lay some foundation. But really, like a demo would help us kind of see all of these things in action. And GA is going to show us a quick, or not a quick demo, but just a demo of how to use this tool in action. So GA, over to you.
Okay, yeah. Let me share my screen. Yeah, can you guys see my screen now?
Yep.
Yes.
Okay, great. So right now you guys are seeing a basketball court, and this data set is the shots that Stephen Curry has made during 2011 to 2016. So all of the shots are aggregated to one single court, and they have some like spatial components as well. So here I just drag it and use calculate. So you can see like all of the shots are aggregated, pre-processed to one single 1 hour. So like it's the 4 quarters of a basketball game. So this data set has the time component. So let's see how we can use the density-based clustering to get a sense of where all the Curry have some patterns of the different areas that he prefers to give the shots during different time of the games. And here in the density-based clustering tool, we put the input points features as all the shots points you are seeing here. We have the output features. And this time I'm demonstrating use the optics, which has the advance that can identify the clusters based on different densities. And then I set minimum features per cluster 20 and the search distance as 200 meters. The time field I'm using is this field you are seeing here. And the search time interval is 1 minute. And for the cluster sensitivity, right now I'm using a relatively low sensitivity, which is 10. The number can range from 0 to 100. So if you increase the number, you have a higher sensitivity. And then you intend to identify more clusters. And here is the result. And this result also have 3 derived charts to help you identify the different, to help you learn and explore the different clusters. And in this time span per cluster chart, you can see all the points are put into the X and Y axis. The X axis is the time field we're seeing, so it's range for 1 hour, and the Y axis is the cluster ID. So for cluster ID is -1, it means they are the noises. And for the positive numbers, they are the real clusters that are identified with the tool. So you can highlight different parts in this chart to visualize different clusters on the map. Like I have select this part. Yeah, so I have selected this pink cluster, and they are highlighted on the map. So you can see Curry at the end of the first quarter, Curry tend to have more shots around the 3-point line and frequently have some goals from the right wing. And if you highlight some other clusters like this yellow one, you can see at the end of the 3rd quarter and at the beginning of the 4th quarter, Curry also have a lot of like 3-point goals. But basically they are like all the range, not like from left or right, but all the like 3-point lines here. And for optics, we also have this reachability chart. So this one, as Ankita has mentioned, you have the ability to select okay. So let me give you more information about this reachability chart. So this one just shows the different part of the cluster as well. So the valleys here means more, the deeper the valley here means the denser the points are. As you can see, this single cluster, if you select all of them, you will like cover basically all the court, but there are different valleys. So if you increase the cluster sensitivity here, basically these 3 different valleys can be identified as 3 different clusters. You see this one is at around the basket, and this one, the middle part. Sorry, my computer is kind of slow right now. Let me make a selection. Okay, let me change to make another selection, maybe. Okay, you see like this valley is basically from the right wing, and this valley is basically from the left wing. And this valley, the most dense part is around the basket. So if we increase this cluster sensitivity, we can let the tool to separate this three part into 3 different clusters. So this is how, like, when I change it to 50, the cluster sensitivity to 50, this is how the same chart looks like. We can put them side by side. You can see like this single part will be divided to 3 different clusters. And similarly for this big green part, it also divided into 2 smaller clusters. So basically optics give you the ability to explore the results with the reachability chart and the time span per cluster chart, and to help you to tweak this cluster sensitivity parameter to get the better results.
Hey, Gia, this is Joseph. This is wonderful. I think some of my colleagues are wondering about this as well. I know one person had a question about this, thinking about, ooh, how can we get students into GIS through sports? How was the basketball court originally digitized? I see it's basically at 0, lat long, so it's not obviously in real world coordinates, but how was that base map drawn? And then how did you get the points to reference that base map?
Okay, so this data set is not originally prepared by me, it's prepared by my colleague. I didn't know like how she like do the preparation. Maybe, yeah, I can give you guys more reference maybe after this meeting.
No worries, thanks.
Yeah.
Cool.
Sorry. Yeah. Okay, so back to Ankita.
Thanks, Jie. I try to answer some of the questions, but if there are more, we can try to answer some of them like either later in the presentation, or we'll just give our like contact details. If someone has specific questions, please feel free to reach out to us. So moving forward to the next, let me first share my screen. To the next tool, we have change point detection. So change point detection, as the name suggests, it's like detects time steps when a statistical property of the time series change for each location in the space-time cube. So it's kind of a complicated definition, but we'll just try to break it down into simpler concepts. The first one is it finds the changes for every location in a space-time cube. So just to kind of give a brief introduction of space-time cube, we have a set of suite tools in our Arcgis Pro space-time pattern mining toolbox that are just to create space-time cubes and run analysis on them. So change point detection is one of the analysis tools that reside in the space-time pattern mining toolbox to help you find patterns in space-time cubes. To give a very quick introduction of what a space-time cube is, so let's say you have points on a map, it has X and Y coordinates, but when you have time associated with each of these points, you can kind of consider it is in 3 dimensions, where the 3rd dimension is the time. So what we do, we use the create space-time cube tools to kind of bin these points in different cubes. So let's say you created this cube. So each cube has a location, an X and Y, and the time that incident happened. So let's say in this example, we have a 10 by 10 cube. So if I have a city, I've kind of gridded the city in a 10 by 10 grid, and then each bin represent a month. Let's say I've aggregated it monthly. So like events that have happened in January, February, March, and in that location is kind of stacked on the top of each other. So here you can see like using the cube, I've aggregated those points together. So if there is like, if this is crime data, I can see that in this location in July, like the most number of crimes have happened. So it really helps kind of visualize that space-time component, because if I had to have just this, like I wouldn't know anything about what's going on in my data set. So it really helps first visualize, and then I can run analysis on it. So let's say I have a location, and every location has a time series. So in January, let's say these number of incidents happen in February and March, so on and so forth. So this is a time series for each location. So in like real life example, COVID example, like how many cases happened in January, February, March, and so on. So you see the time series, and what this tool will do is it for each location in your space-time cube, it will try to find where changes have happened at a location in your time series. So for example, again, going back to the definition to kind of, I think it'll make more sense now. It detects time steps when a statistical property of a time series changes for each location in a space-time cube. So the three changes that the tool is able to detect are the changes in mean. So if you have a time series for a location that looks like this, you can, like right now using our just like visual representation, I can see that the mean for this is different for the mean for this time segment. So this is kind of change in mean, but the tool will be able to detect those changes. So this is a very quick visualization of change in mean. Again, the tool can also detect change in standard deviation. So let's say we had wind velocity for each location. So it was kind of very consistent, and then something changed, and then the wind speeds were crazy. And then here, like it kind of settled again. So here, like we can see that the changes in standard deviation, the tool will be able to detect them if you ask the tool to detect change in standard deviation. And then there's count. Count is very similar to mean, like you can kind of see that the things have changed, but the difference is that mean is for continuous variables, like you have temperature values, it kind of has a continuity to it, but count is like the discrete values, like how many incidents happen of COVID cases in this month. So that is the distinction between mean and count. So count is continuous and it assumes normal distribution, and mean is continuous, it assumes normal distribution, and count is discrete. So let's quickly look at an example. Let's say if you chose the tool to find changes in mean, what would it do? So here I have an example time series. This is what it looks like. What the tool will do, it will detect change points where the statistical property, which is mean in this case, has changed. So here, each time series or each segment, now we have like these three segments in our time series. Each segment should have a constant mean, should have a normal distribution, and within each segment, the standard deviation should be the same. So if you're looking for changes in mean, the other two statistical properties like should remain constant. So here, let me see. I don't know why I hit this slide because it's very important. So here I can see that in each of my time segments, here the mean is constant. The standard deviation is pretty much the same for each segment. It's kind of equal to or very close to 1. So it's a good assumption. And if I plot individual time series, the normal distribution, you can see that all the three segments have a very similar and normal distribution. So it's a very good example of splitting this time series into 2 or 3 segments using 2 change points where the statistical properties follow the assumption of a mean shift. But how change points are detected? So I just gave an example that if the tool detected these 2 change points, that would be perfect. But how are they really detected? So let's consider the same example, 2 different scenarios. In scenario 1, we'll do the same thing we did earlier, split it in the places where we think the mean is changing. In the other example, we've split the time series or kind of detected change points in the places that aren't really change points, because like here, you see that the mean hasn't really changed over time. Like it's very constant, but it has really changed at this location. So let's consider these 2 situations. In example 1 or scenario 1, each segment follows the assumed distribution very clearly. Like you said, it has constant mean, normal distribution, and the standard deviation is very similar across different segments. So when each of the segment, they follow the assumed distribution, the overall cost of segmentation is low. So when you create cost for each of the segmentation, it's very low because it follows the assumed distribution. On the other hand, when we split it in awkward places, we'll see that here the standard deviations are very dissimilar, are very different. And here, like the second segment, it doesn't even have a normal distribution. So when you split it in this way, there's a higher cost of segmentation because it's not following the assumptions of the distribution. So when we compare these two, scenario one is more optimal. And that's how the tool will say that pick the scenario one, because the cost of segmentation is lower because each of the segment is following that distribution, the assumption of the distribution. So in this case, this will be selected. So when we say like we kind of split it in three, we find those splits and we call those splits as change points. These are the points where the statistical property of your time series has changed. But how many change points are optimal? So let's just take the same example. If I add another change point, like let's say at the end of this time series, and I split it in now 4 time segments, each of these individual time series does follow the 3 assumptions. So it's not that based on the cost, what is better, like 2 or 3, because the more change points you add, the cost of segmentation would go further down, because like each of the segmentation is now small and it has, and each of them is considering or follows the 3 assumptions of the distribution. So if I had to add more and more and more change points, the cost of segmentation would go even down. But then the relative, if you look at the relative thing here, I have too many change points. It's not useful for my analysis. Even if the cost of segmentation has gone down, it might just have gone down by like 0.001 or 0.002. That cost of the lowering of cost of segmentation has made it more complicated to make any useful decisions here, right? Because now you have too many change points. So how can you make it more useful? So to limit the number of change points that you can have, there are 2 ways. One way is to have the defined number of change points. So let's say you know that in the year 2021, you're looking at the time series and you introduce 2 big marketing campaigns. So you want to analyze the changes in the mean sales values based off of 2 marketing campaigns. So you can just say, I need to find exactly 2 change points in my data set to find, like after those marketing campaigns, when were the times when the change actually happened. So you know how many change points you want to look for in your data set. So that will limit the number of change points the tool will produce, because then you know exactly how many change points you need. The second method is the auto detect number of change points, also called the PELT method. So in auto detect, what happens is we add a penalty every time the tool adds another change point. Let's say it added another change point, we add a penalty value to the cost of segmentation. So basically now it's the math, like, is the cost of penalty more than the lowering cost of the segmentation? So if the cost of segmentation only improved by, let's say 0.01, but the penalty is like 0.5, then it's not a good decision to add a new change point, because the cost of segmentation is not it's not improving a lot, but the penalty is too much. So that could help us prevent adding additional change point if we add penalty to the change point. But if you add an actual change point, then the cost of change point would be lowered way further down and the penalty wouldn't affect that much. So again, there's a cost associated with adding new change points. And we can kind of tweak the penalty in our tool. So if you have higher penalty, then less number of change points would be detected, meaning the tool has a low sensitivity towards change points. So you'll find some of the places that could have been a change point, but then since the penalty to add a change point was high, the tool didn't detect it. So the sensitivity is low for change points. So on the other hand, if you have lower penalty, the sensitivity is high. So if adding the cost of another change point is low, then more change points will be detected. So in the tool, there is a parameter called sensitivity parameter that you can tweak to say, do I need low sensitivity? Do I need more change points, or do I need high sensitivity? So yeah, those are some of the parameters in the tool and how it works, kind of summarizing what the difference between the 3 methods I have. So in the first method, change and shift, these are the three assumptions that each segment has to follow. Like the mean is constant, the normal distribution, and the same standard deviation. When you're looking at standard deviation changes, there should be constant standard deviation across in each segment, and the segment should be normally distributed, and the mean should be same for all the segments. And for count, it's very similar to mean. It's just it has a Poisson distribution and not normal distribution. So the way the three works, they're exactly the same. I talked about mean shift, but the assumptions change based on whatever type of change point you're detecting. So with that, Gia is going to show us a demo of how we can use change point detection in action. Over to you, Gia.
Yeah, thank you. So yeah, I just saw a question. Some people ask like if we can use slope to identify the difference. Yeah, so actually it's a upcoming enhancement. Yeah, it's probably will be in the next release. Yeah. Okay, so. Yep. So here is the example that I will show you guys with the change point detection tool. So right now you are seeing the living atlas map of all the like 150, the largest ports in the United States. And it has, and we have already like aggregate those count of the cargo ship into a cube, space-time cube. And this time we'll use, and it's stored as the analysis variable cargo non-zeros. And this time we'll use this the count, the change type, the count to analyze all the change points detected, to detect all the change points. And the method here we're using this pelt, as Ankita has mentioned, is automatically detect all the change point at each location. So each location by location decision about how many change points will be detected. And the detection sensitivity is 0.25 here. So the range will be between 0 and 1. So it's very similar to the clustering sensitivity of the density-based clustering tool. And 0.25 is like a relatively low detector sensitivity here. And I've already run the tool. So the tool is relatively quick to run, but I have already saved the result here. So the output is symbolized with the number of change point detected at each location. The darker the color, the more change point detected at that location. So we have seen some very interesting result in, sorry, my cats, I need to let her go. Okay. So here we have seen some interesting results. Let's check the pop-up of one of the darkest points here. As you may have already seen, we have a lot of like pop-up in our space-time pattern mining tools. The pop-up usually have this time series, whole time series mapped out. So you can see the blue color, the blue lines is the original value, and all the change points detected are marked by this bright pink circle. And you can also see the mean of each section as these vertical lines here. So basically this part, you can see very dramatic change happened during September 2019, where the change point is detected at the beginning and at the end of this section. So basically the mean jump up really quick and is keep as a very high value, even if there's some like change, but it's consistent as a relatively high value. And then all of a sudden at around this time point, all of the cargo ship counts jump down to its original values. So basically there should be some very fundamental structural change happen at this time period. And we can also notice another section here. So if you have eyeball picking up some like the change point, maybe you cannot pick up this section because it's just look like some spike. But if you look closer, there are some consistent change, which like the high value consistently lasts for maybe 4 4 time steps. So this part is also detected as a change point at the beginning and at the end of this time period. Compared to other specs, you can see they are just like mostly like outliers. They just jump really high and then goes back. No very consistent change. So this part is really can tell us the tool can pick up the change point compared to just to like pick up some random outliers here. Yeah, and we can also check some other like locations where only 0 or where no change points or only 1 change point detected. You can see this one is just like the mean shift up a little bit. And this one is detected as a change point. You may also ask why this part is not detect any change point, because it seems like it's jumped really high. So I think if you change the change type to other thing like the standard deviation, this part may be picked up as some change points. But if you're using count, basically there's more like if the mean is shifted. And this part, we can see some high value, but it's not some consistently high value. It's just the jump up and down, jump up and down. So with a very low detection sensitivity, we don't pick up any like change point at this section. And you can also like check other locations, like this one, just to pick no change point. And we can also see some other areas and how the data looks like in San Francisco. This place, we have a lot of like ups and downs. The data, the time series really like change more frequently than Philadelphia. So as you can see, like each section is relatively small, but we can see the change points that just detected at every like mean shift a little bit, jump up and down. So maybe by eyeball seeing, we just don't pick up so many change points, but this tool can like automatically choose this location should be more fundamental structural change by picking up, yeah, those change points. Yep, I think that's it for this demo. And Kita.
Yeah, I'm sorry, I think we had another demo lined up, the presence only prediction, but since we are kind of running out of time, we can definitely share some resources about it, and GA is gonna write a blog post on it with the example. So we will definitely share that with all of you. So in the end, I'm just gonna share a slide which I have to bring up, but you can wrap up, Dr. Krisky, and I can share the slide in the meantime.
Oh, feel free. This has been wonderful. Just like I suspected, we have this much content in this much time, but maybe we can have you back later this year.
Yeah,
we'll
be happy to be back. And
there were a few questions that we did not get to, but yeah, go ahead and share that next steps and how to dig deeper and how to keep learning about this. Thanks so much.
Sure. I think I closed that presentation, but I'm just gonna quickly bring it up. But in the meantime, yeah, please feel free to connect with us on LinkedIn, or I mean, if you have any questions, we're always happy to answer those questions. And yeah, got the slide, so I'm gonna share my screen. Okay. So here, there are a couple of resources that you can look at. The first one is the Spatial Data Science MOOC. Like the MOOC really helps like with, like it's a 5-week MOOC, and it helps you with like each and every tool that we probably didn't cover, but there were more tools, and then help you with the examples and the process and the algorithms behind it. And there's learn.arcgis.com with a lot of learn lessons, but we also have our own spatial statistics website, that an ArcGIS hub website that has all these resources, like these presentations, some learn paths, like some examples, like hands-on learn lessons and examples. And I think that's a great resource for all the content that we have showed today. And we have a couple of new blog posts, like what's new in spatial statistics for Arcgis 2.9, 2.8. Some of the tools we covered, some of the tools we couldn't cover are also listed in those blog posts. And then introducing data engineering in Arcgis Pro is a blog post that has like step-by-step process that you can do with the example that I showed you about data engineering. And GA is also working on the presence only prediction blog post. So once that's out, that will help with the examples and the process, how that works.
Oh, well, many thanks, Gia and Ankita. It's been wonderful. And to me, it cuts right to the heart of why we all care about GIS and why we feel it's such a valuable teaching tool. Getting students to look into patterns of space and time, changes on the Earth's surface, and some wonderfully creative examples of using sort of maybe out of the box examples of how to get students engaged with all of this. So many wonderful gems that you've shared, just in approaches, but also in the tools themselves. So again, many thanks for sharing with us right after the first of the year. What a great way to start the new year.
Absolutely. Thanks for having us. And I'm so appreciative of the comments and the chat. It was so interactive. I love that fact that people were asking questions. So if you have more questions, again, feel free to reach out. But thank you so much for having us today.
Oh, it was wonderful. And I would just say, in terms of building the community and having this kind of dialogue, that's exactly what those MOOCs are for, folks, is that you're going through the MOOCs with a cohort of others. And so you're connecting with others as you progress through the content in the MOOC that Ankita shared, but also the other MOOCs. So I just want to lend an additional thumbs up to the MOOC experience. Okay. I'm going to stop the recording right now, so we will have this archived. And again, thanks to both of you for sharing. And Kansarina and I were, now you folks on here can understand why we were so excited about this. So again, wonderful content. Thanks so much.